Here's a question that sounds simple but quietly breaks most models. How do you teach a network that two photos are the same person when you have thousands of people and only a couple of pictures each? You cannot just classify them. There are far too many classes and far too few examples per class. What you actually want is an embedding space, a map, where the same person sits close together and different people sit far apart. Triplet loss, made famous by Google's FaceNet back in 2015, shapes exactly that kind of space. And it does it with a surprisingly clever move, comparing 3 examples at a time instead of 1. Let me show you the mechanics. Before the how, let me frame the what by contrasting 2 very different training goals. A classification loss learns fixed boundaries. It carves the space into named regions, 1 per class, and asks which region does this input fall into. That works beautifully when your classes are few and stable, but it falls apart when they are many and always changing, like every face on Earth, most of which the model will never see during training. Triplet loss throws out absolute labels and learns relative distances instead. Its only demand is that similar things end up close together and different things end up far apart. It never has to name anyone. Shape the geometry of the space that way, and afterward a simple distance threshold is enough to verify whether 2 faces belong to the same person. So how does one training step actually work? Walk through it as a loop, 1 triplet at a time. Pick an anchor, a reference example, say a photo of person A. Then grab a positive, which is another photo of that same person A, and a negative, which is a photo of someone else entirely, person B. That is your triplet, 3 examples chosen together. Send each of them through the network to get an embedding. Now you have a set of points in the space, and you can measure how far the anchor sits from the positive and from the negative. Pull the anchor toward its positive and shove it away from the negative. Over many steps, the 2 examples of the same person collapse together into 1 tight cluster, while the different person is driven off to the side, out of the way. Enforce a margin, and this is the crucial part. The anchor must be closer to the positive than to the negative by at least a set gap, not just barely closer. Without that gap, the model would happily settle for a razor-thin difference and learn a sloppy, useless space. Let me boil the whole thing down to 3 ideas that make triplet loss tick. It works on a triplet, an anchor, a positive of the same class, and a negative of a different class, 3 examples judged together. The loss pulls the anchor toward the positive and pushes it from the negative, and insists on a margin between those 2 distances. Mining is absolutely essential because most random triplets are already easy. The negative is obviously far away, so they give 0 gradient and teach nothing. You have to actively feed it the hard or semi-hard triplets, the ones the model still gets wrong, or it simply stops learning. Alright, let me leave you with the things worth locking in before you go. Triplet loss shapes an embedding space where similar items are pulled close and different ones are pushed far apart, purely by relative comparison. It compares a trio at once, an anchor, a positive of the same class, and a negative of another. A margin forces the anchor closer to the positive than the negative by a real gap, not a tiny one. Mining hard triplets is what keeps it learning, and the payoff is embeddings where a distance threshold verifies identity. If you like seeing the machinery of modern AI laid bare like this, more is waiting for you at standarity.com.